Hello everybody! Welcome to our video solution to problem 1 from Quiz 8. This is Fall 2023 Math 307 Linear Algebra at Cal State Fullerton. And in this problem we are reminded that you can form the transpose of a matrix, in this case a 2 by 2 matrix, by reflecting across the main diagonal. So, in this case, for example, you can see here we have AD along the diagonal, and when you take the transpose, you still have AD on the diagonal. However, the B and the C have been swapped, right? So that's the transpose of a 2 by 2 matrix. And we're asked to prove that the function which takes the transpose of a matrix, right? So you take A and replace it by A transpose, which is a function from the vector space of 2 by 2 matrices over the reals to itself. We want to prove that this function is an isomorphism. Of course, first thing, we better know, well, what does it mean to be an isomorphism? So we have two pieces here. First, this really should be a linear map. And the second is that this needs to be a bijection. Okay. All right, so we have two things that we need to show here. So why don't we start with showing that it's a linear map. Now, I'm actually going to do this in two separate ways. One of them is a very straightforward way. The other is a little more clever using the universal property of a basis. So let's do it first just using the definition of linearity. So a function is going to be linear if it's both additive and homogeneous. And let's just show them separately for simplicity. So let's say I had A plus B, and I'm going to compute the transpose. Well, I've already defined a capital A up here. I guess I need to have a B, so we'll just copy our A. It's going to be A, B, C, D, and then B, maybe this will be E, F, G, H. Okay, so if I compute A plus B, this is going to be, let's see, you do addition component-wise, so this will be A plus E, B plus F, C plus G, and D plus H. And now if I compute the transpose of A plus B, well, I get to keep the diagonal, so A plus E and D plus H remain, but I'm going to swap the off-diagonal entries. So C plus G moves to the upper right, B plus F moves to the bottom left. All right. Now, if I'm going to be showing additivity, then A plus B transpose is supposed to equal A transpose plus B transpose. So let's compute A transpose. Well, I actually have it up above. This is going to be AD, CB. And how about B transpose? Well, I keep the E and the H on the diagonal, and I swap the F and the G. Now, I want to show that A plus B transpose, right, which I've already computed, is equal to the sum of the transposes of A and B, so we better write down the sum of the transposes of A and B. Well, I just add these component-wise, so I get A plus E, I get C plus G, B plus F, and D plus H. Oh, and look at that. These are exactly the same. So we have additivity. All right, so next we need homogeneity. So what if I was going to take some, I don't know, how about we'll call it gamma in F, and I'm going to multiply A by gamma and then take the transpose. F, by the way, here is, of course, the real numbers. Okay, well, let's see. The way you multiply a matrix by some constant is you just multiply each element by that constant. So let's see here. This is going to be gamma A, gamma B, gamma C, gamma D, and then I need to take the transpose. Okay, transpose, I keep the diagonal, so gamma A, gamma D, and then I swap the off diagonal. So I'll have a gamma C up top and a gamma B down below. All right, well, let's pull this gamma out. All right, I have a gamma in each term, so there's gamma times A, C, B, D. And wouldn't you know it, that A, C, B, D, that's exactly our A transpose. So this is gamma A transpose. So this tells us that the transpose map is homogeneous. All right, if I take the transpose of a scalar multiple It's the same thing as taking the transpose and then multiplying by that scalar. Okay, so this is a very naive, straightforward way of showing the linearity. Let me show you a second method. So this is where we're going to use the universal property of a basis. Universal property of a basis says, if you know what a function does to the basis, then it's going to extend uniquely to a linear map on the entire vector space. So what is a basis for the 2 by 2 matrices over R? Well, let's just say I had some A, B, C, D. Then I know I can write this as A in the upper corner, 0, 0, 0 in all the rest, plus 0, B, 0, 0 with a B in the upper right, plus 0, 0, C, 0, so now C's in the lower left, and then finally 0, 0, 0, D, with D is in the lower right. And then from each of these I can pull out that constant. So I get A times 1, 0, 0, 0, plus B times 0, 1, 0, 0, plus C times 0, 0, 1, 0, plus D times 0, 0, 0, 1. Right. You might recall in class I mentioned a few times, right, we had names for these. The first one was E11, this next one is E12, this is E21, and the final one is E22. All right, so now all I need to know is what the map would be doing to these basis elements, and if that coincides, right, if that's going to work with what we defined up above, then that must be the unique linear map. So what is the transpose of E11? Well, I look at E11 and I have 1, 0 on the diagonal. 0, 0 on the off diagonal. If you take the transpose, the 1, 0 stays on the diagonal. The 0, 0 swaps, but that doesn't change anything. E11. What about E12 transpose? Well, in this case, the 0, 0 on the diagonal stays, but the 1, 0 on the opposite, on the off diagonal, that actually is going to swap, and it gives me the same thing as E21. And E21 is just going to go backwards. So if I have E21 transpose, I'll get E12. And then finally E22 transpose will just be E22 again, because again, the only non-zero entry is in that lower right corner on the diagonal. That doesn't get moved by the transpose. Okay, so now we know what happens, right, to this basis, which means there is a unique linear map that's going to extend this, right? So now, if I had A E11 plus B E12 plus C E21 plus D E22, oops, I missed an E, E22, and I apply the transpose of that, then I know by the universal property of a basis, this is going to equal A E11 transpose, which is just A E11, and then B E12 transpose. But E12 transpose we set up above as E21, so this would be B times E21. Then the transpose of C E21, which is just going to be C times E12. And then finally D times the transpose of E22, which is just again D E22. Okay, so here this is by the universal property of a basis. Oh, and this is exactly how we actually define the transpose, because here we have A E11, B E21, so we put a B down here, C E12, and D E22. All right, so this is a little stranger of a way of doing it, and if it's not, obvious what's going on here, right, like that's not surprising the first time you see it. The whole idea is if you can show that the way you've defined your map on all elements is what would happen if you extended the map based on what you just defined on the basis in a linear way, then by the universal property of a basis, that actually must be a linear map, because there is one way and it always works. All right, so in either case, we've concluded, all right, so we now know that the transpose map is a linear map on the vector space of 2 by 2 matrices over R. Next, though, we want it to be an isomorphism, so we have to show that it's a bijection. Now, because this is a linear map from a vector space to itself, in order to show you have a bijection, it's enough to show that you have an injection. Or, if you like, it's enough to show that you have a surjection. Either one of those. I'll do both, but we only have to do one. This is very important, right? We didn't have to do both here. So, let's show first that the transpose map is injective. Now, in order to show that a linear map is injective, it's enough to show that the null space of the map is exactly the 0 element. So, let's try to compute the null space of the transpose map. Well, let's see. The null space is going to be all 2 by 2 matrices, so we'll write A, B, C, D, in mat 2 by 2 R, such that the transpose of this matrix is equal to 0. And in this vector space, the 0 is the 0 matrix. Oh, but what is the transpose? The transpose is A, C, B, D. So we just want to find all the matrices such that A, B, C, D is equal to 0, 0, 0, 0. But of course, for this to hold, you need all of the components to be the same. So A has to equal 0, C has to equal 0, B has to equal 0, and D has to equal 0. Oh, well that just means that this is the 0 matrix. Wait a second, that means that the original matrix is the 0 matrix. Ah. That means you get just a single element in your null space, namely the 0 matrix. Okay, so if the null space, though, is equal to the 0 element, this implies that the transpose map is injective. But again, because we're working, right, from a vector space to itself, and we're in finite dimensions, this implies that the transpose is a bijection, and hence is an isomorphism. All right, so we're done, right? But let me do it the other way, right? Just in case you tried to show the surjectivity, I'll show you what you could have done if you struggled with that. All right, so how do we know that the transpose map is surjective? Well, remember, surjective means that every element in the codomain has a preimage. So let's just choose something from the codomain. Well, the codomain, actually, and the domain are the same. It just means choose a random 2 by 2 matrix. So we're going to let A, B, C, D be a 2 by 2 matrix over the real numbers. So all I need to do is find a preimage. Well, this is pretty easy. I need to find a matrix whose transpose is equal to A, B, C, D. Well, we just take the transpose of this matrix. A, D on the diagonal, C, B on the off diagonal. What is the transpose? Let's see. The A and D stay in the same place. The B and the C swap. And there we go. All right, we have found a preimage for A, B, C, D. Therefore, this transpose map is surjective, which implies bijective. And again, this implies we have an isomorphism. So either way, we're in good shape. All right, so there's lots of different approaches, right, to handle some of these questions. Okay, obviously I'm not expecting you to do all of these different approaches. You know, pick one for the linear map, pick one for showing the bijection, and it's actually a pretty reasonable proof at that point. All right, everybody, we will see you next time.